Welcome back. It's now time to look at one of my favourite applications of fused filament printing, Polypills. Most commercial printers have the capability to print multiple filaments simultaneously, usually 2 or 3. This means you can create tablets with discrete sections, each made from a different filament. We realised a few years ago that this meant fused filament printing was ideally suited to making polypills. On the screen are 2 designs of printlets, each made from 2 filaments. The top design has multiple layers, while the bottom design has a core of one material surrounded by a corona of another. It is possible to fabricate these printlets with different drugs in different layers, or the same drug in different grades of polymer, or different drugs in different polymer grades. However you do it, I think you'll agree that the technology is ideally suited to polypills. This photograph shows the actual printlets we made from those CAD designs. On the left, the multi-layer design, and in the middle, the core shell design. Obviously, with the core shell design, you can't see much looking at the outside. So the image on the right shows a cross-section, and you can, just about, make out the core and the shell. We tasked a research student with drug loading these printlets, and they chose to use caffeine and paracetamol as model drugs. I presume they were thinking of the ideal polypill for a student revising for an exam. Paracetamol to ward off the headache caused by stress, and caffeine to enable staying awake for the 24 hours prior to the exam. You know you do that. When we print these formulations, we can't know for certain where the drug is actually located within the tablet, so we characterise them with a range of techniques to find out. One of the best techniques is Raman Mapping, which is done by my friend Richard at the University of Bradford. Raman spectroscopy is laser-based. A laser beam is focused onto a sample where the light interacts with the molecules present and is then reflected back to a detector. The resulting spectrum is characteristic of the molecules in the material. By moving the laser over the surface of a sample and recording the Raman spectra, it is possible to create a map of the surface, and the maps are shown on the screen. The beauty of the technique is that it is possible to colour-code the spectra against reference data. In this case, paracetamol is coloured red and caffeine is coloured green. You can see in the images, which show cross-sections of the printlets by the way, that in the multi-layer formulation the drugs are indeed in separate layers, and in the core shell formulation the caffeine is in the centre while the paracetamol is in the corona. As you might imagine, the dissolution behaviour of these printlets should be different. In the multi-layer formulation, both drugs are exposed equally to dissolution medium, while in the core shell formulation, the paracetamol is exposed first, while the caffeine is shielded in the centre. And indeed, this difference was seen in the dissolution data, where you can see both drugs are released equally from the multi-layer formulation, but sequentially from the core shell formulation. I think I hardly need to tell you that this is yet another way that 3D printing enables the personalisation of medicines. That's all very good, you might say to me, but can you print a polypill that is clinically relevant? Let me think about that for a minute. Oh yes, remember the study I mentioned earlier about blood pressure medication? In that study, the authors found that giving patients 4 different antihypertensive medications at the same time was way more effective in controlling blood pressure compared with taking a single medication. The problem, of course, is the excessive pill burden placed on the patient, and I can tell you that non-adherence to blood pressure medication is the main reason patients go on to suffer coronary problems. What would be ideal then would be a single tablet containing the 4 antihypertensive drugs used in the study, all at the correct dose. Then a patient has only to take 2 tablets per day, one in the morning and one in the evening. Can such a tablet be made with 3D printing? It would be rather a letdown if I said no. On the screen, you can see the polypill that we developed. It contains 4 layers, with each layer containing one of the antihypertensive drugs, all at the doses used in the clinical study. Pretty neat, I hope you'll agree. Now you might say to me, does it matter which drug is contained within each layer? And I would say yes. The reason is because the surface areas of the top and bottom layers are much greater than the surface areas of the middle two. The top and bottom layers have both an edge and a circle exposed to water, while the middle two have just an edge. Since drug release is often influenced by surface area, it certainly does matter which drug is in which layer. This is why there are two types of polypills shown on the screen. They contain the same drugs in the same concentrations, but with the layers in a different order. Of the 4 drugs in the polypill, atenolol has the highest solubility, and thus it will tend to dissolve the fastest from the tablet. When we measured the rates of drug release from the polypills, we saw the profiles you can see on the screen. In the type 1 polypill, atenolol is in the top layer. Thus, as well as having the highest solubility, it is also in a layer with the greatest surface area, and this meant it was released much faster than the other 3 drugs. That is shown on the graph on the left. The other drugs have relatively low solubilities, by the way, which is causing their release profiles to be quite similar and independent of surface area. By moving atenolol to one of the inner layers, as in the type 2 polypill, you can see that the release of atenolol is slowed down, and the profiles of the 4 drugs are much closer, shown in the graph on the right. This then is yet another way in which 3D printed tablets can be designed to engineer specific release profiles. In this case, we want all 4 drugs released at the same rate, so the type 2 polypill is best. But there may be other instances where one drug needs to be released before the others. Right, now we've talked about polypills, I think we should consider poly coffee breaks. When we come back, we will finish the lecture by looking at laser-based and gel printers. See you in a bit.